Okay, so now we're going to discuss systems and models. So this is an important part of the class. It's called Environmental Systems and Society, so there's going to be lots of systems, obviously. We're also going to see lots of models, which are moshing, right? This is something that we will see in many chapters, and in fact, most chapters, we're going to deal with both. It's kind of just a way that we view a lot of this information. Okay, and to start off, we're going to look at vocabulary once again. We're going to look at word parts. It's a smaller list this time, but these are words that we're going to come across in this unit. One is this prefix trans, which means across. Okay, and then the suffix, we have fer, which means to carry, and then form, which means shape or form, right? So what does this mean in actuality? We might see this word transfer. Well, we put that together, okay? Across, to carry across, right? So that's the meaning of that word, essentially, transfer, okay? And then transform, very similar, but it means to change shape or form. Okay, we have this word here. Okay, so that the goes from one form to another, changes the form. Okay, when it goes across. Okay. Sorry, that's for my regular class. This is for us. So let's review again. What is a system? Okay, so it's a work of parts. Excuse me, a set of parts that work together to make the whole function. And generally, the whole is more efficient than all of the parts. So again, we have this subway example. All the parts together, you will get places quicker than if they were individual. Another example of this is a bike, right? A bike, these are individual parts, but when you put them together, they become a bicycle, right? And now this bicycle is much more efficient than these individual parts. That's why we do it. So this bicycle can be considered a system, just like your computer is a system, just like your body is a system. So many things can be considered a system. So it's a way that we view the world, and it's going to be a way that we view this material. Now models are a little bit different, okay? Models are a simplified version of reality. They can represent a system, object, or concept. Okay, so we might be familiar with this model. This is an atomic model. So we know an atom. Okay, this is a very simplified diagram that helps us understand, the nucleus and the electrons, okay, and the electron rings around it, so we can understand it much better. This is closer to what the electron rings look like in real life, okay? It's a little harder to understand, right? This is kind of closer to reality. This is the model that we use to understand it. Now, there are pros and cons of this, but one of the big pro, I would say, is it just makes things easier. It's easier to understand, okay? So, again, pros and cons of models. Let's go through it now. One of the pros is you can understand complex environmental issues easier, right? And it gives us a holistic or whole view of a situation, okay? So, if we think about the environmental systems, we're looking at it from a very high up perspective, and we can see how all these individual parts work together, right? So how these little niches in an ecosystem interact with each other, interact with their surroundings, with the atmosphere, with the soil, things like this. We're able to see the whole thing, and that helps us understand things a little bit better. And it can help us predict what will happen if a change to a system occurs. So again, if we look at a food web as a system, right? What will happen if we take one animal out of that food web? Well, we can predict just based on that model what will happen. Oh, this animal will grow in numbers. Oh, this animal may die off completely. Okay, it helps us predict. Some of the cons is that it's oversimplified, right? A model is maybe used to help us understand, but sometimes we're seeing a inaccurate view of reality. So, for example, if we look at a food web in an ecosystem, again, a simple view might only show 10 animals. We see how they eat each other, for example. But in reality, in an ecosystem, there might be thousands of animals. And it's harder to predict what will happen if we pull one animal out of that big, huge 1,000 animal food web. But if we just see 10, we can understand better, but it's maybe inaccurate. There's a lot more that might happen that we just don't see because we don't see the whole picture. It's too simplified. It can be inaccurate in its details. Okay? The same data can be used to create different models. So again, if we're talking about food webs, a food web we might choose these 10 animals to see how this ecosystem works. But using the same ecosystem, we could choose 10 different animals. We might see a whole different view of that ecosystem and might come to different conclusions, right? Same thing with atmospheres and atmospheric data. We can create atmospheric models. We can predict what will happen in the future using the same information, but with different models, we might come to different conclusions. That's why you might hear about, like, a TV station has their atmospheric model, but then like a scientist has a different one and a different scientist has a different one. They're all using the same information from the past, but they come to different conclusions. That's kind of the point here. And again, models are limited in their ability to predict, especially long term. Again, it's because it's a little bit inaccurate, a little bit oversimplified. That's the con. Now let's talk about these two terms, which is reductionist models and reductionist thinking, and holistic thinking or systems thinking. So systems thinking, again, is the top-down approach. Reductionist thinking is looking at the individual parts in it. And we will do both in our class. Sometimes we will focus on maybe a single thing, like a small part of an ecosystem, because we want to learn more about just something specific to it. Maybe the composition of soil, for example, in an area, right? Or we can look at the whole ecosystem and the different parts within it to get a different view of it. And we're going to do both in class, essentially. Here we have, remember what we said? The same data can be used to create different models. This is an example of that, okay? So this is the Shanghai subway system, like we saw. The one on the right is much simpler, but more inaccurate than the one on the left. The one on the left is harder to understand, but more accurate, right? So we have the same data, where these subway lines are, but we created two different representations, two different models to show it. And both have their pros and cons as a result. Okay? Now, again, let's do a quick review of systems diagrams, but we'll go more in depth to it. There's a reason why we're doing this. Again, the arrows are your inputs. The outputs going away from this box. The box is your storages, right? So inputs, outputs, storages, right? The arrows are kind of the flow of energy and matter, okay? When it comes to environmental value systems, your inputs could be politics, education, culture, religion, media. The outputs could be your decisions, okay, and your courses of action. So maybe you grew up in a household with a mother who cared about the environment a lot. That's probably going to change your environmental worldview quite a bit. And that will change your decisions and your actions and your opinions in the future. And that's kind of the point of this. Okay, let's see here. Nope, we're not doing that. That's again for my class. We are going to do this. We're going to talk about large or systems existing at different levels. 'Cause remember we said systems can interact with each other. They can also exist at different levels. And that's one of the bigger ideas from this chapter, from this unit. Okay, so this is an example. On the large scale at the top, we have the solar system, right? That's the biggest system. Then smaller than that, we have the Earth. The Earth is a system with many different parts. And then we might have smaller than that, a specific biome as a system. So biome is like a type of environment, for example, a rainforest or a temperate forest or a desert, something like this, taiga. These are all types of biomes. Beneath that, we might have a specific ecosystem as a system. Again, we've never seen this word ecosystem, but if you remember from our past video, eco means nature, system, shitong, this is the all the different parts working together, so we can kind of guess, right? This is a system of the environment, right? It's a small area where the environment is, right? That's kind of a very simple definition of what an ecosystem is, but it kind of gets the point across. So again, learning these word parts helps in this situation. An example might be the Amazon rainforest, or like a part of the Amazon rainforest, right? That might be considered an ecosystem. Now, even smaller than that, we might think a riverbank, the edge of a river within the Amazon rainforest. Within that, we have plants on a riverbank on the Amazon River, and then within that, we have leaf of a plant on the riverbank on the Amazon River. So systems, because again, this leaf is a system. It's got parts, right, that work together. These all kind of work within each other, from large scale to small scale, and that's a big point. Now let's talk about open systems versus closed systems. So an open system is, if we see in this picture, we can exchange matter or mass and energy or heat. Okay? So, for example, I'm going to pull this out. All right, it's just been kind of sitting here. I have a glass of water. It's kind of carbonated water, but it is what it is, right? This is an open system. I can pour the water out. That's mass leaving. But also the heat will transfer. If it's cold at the start, eventually it will warm up because the temperature of the environment around it will transfer heat to it, and it will transfer heat, or its coldness, to the environment around it, right? So that an open system is very common. It's probably the most common type of system, right? This is what we mostly see because most things transfer heat and energy, right? Or excuse me, heat and matter. My mistake. Now, there are also closed systems and isolated systems. Closed systems only transfer energy or heat. So you could consider this. So this is a can of carbonated water to be a closed system. Why? Well, no matter can really get out of it, but the heat will eventually get inside of it, warm up the liquid inside of it, and the cold liquid inside of it will eventually warm up, heat up the can on the outside of it, heat up the air around it. So it is transferring heat because really most things transfer heat. That's kind of what happens, right? Now, this is just, again, a model of a closed system. In reality, it's not actually a closed system because over the long term, in a long period of time, eventually mass and matter will leave it, okay? The gases inside of it will kind of go through the molecules inside this can, escape. So in that sense, it is not a perfectly closed system. And most things, in fact, basically everything is not a closed system. In fact, you'd have a hard time finding a closed system. The closest example we have is the Earth. The Earth can kind of be considered a closed system. Also, these geochemical cycles, these are also considered maybe closed systems, but they're not really. The reason why is because the atmosphere connects to space, right? So all these chemicals and all these systems are within the Earth, but they also leave into space, and things from space come into the Earth. So in reality, it is also an open system. Just closed systems exist only kind of in experiments, okay? They don't really exist in reality. And that's kind of the main point. Really, almost everything is an open system in reality. Finally, isolated systems exchange neither. And again, this is kind of in theory. You could consider the universe maybe to be an isolated system, but we're not sure on that. There might be multiple universes. We're not sure at this time. So, but in theory, the universe might be an isolated system. It's not exchanging heat to something else or taking in matter. Okay. Oh, I thought I deleted this. Interesting. I'm going to skip to this. And we're almost done. Okay, so emergent properties. So emergent properties are kind of these things that happen in systems when you combine these individual parts. So again, I said systems become better than the individual parts. What happens is maybe something comes out of that system that is greater than the sum of its parts. And that something is what we call an emergent property. Okay? So the interaction of the parts creates something that they could not produce independently. So an example of this may be a group of trees in a forest. Let's say we create this forest. It can create new habitats for animals and new niches for animals and bugs and plants that an individual tree cannot. So once we get all these trees together, the combination of sunlight and soil composition and rain hitting the floor will create new habitats that an individual tree cannot. So the new property that comes out of a system that cannot be achieved unless it's a system is called an emergent property. It's like a new, emergent means to come out of. It's a property that comes out of the system that otherwise would not exist. Okay, so we might ask, what's the emergent property? Oh, almost done. What's the emergent property of a subway system? So we put all these subway lines together. What's the emergent property? Well, you get places quicker, right? If there were just one line, if there were just one subway line, and you need to go to this lower right-hand corner, and you could only take the yellow line here, you would get to the end of the yellow line, and then you would have to walk over to this lower right-hand corner to the airport. Whereas here, in the subway system, you can just transfer lines and get there, go from the yellow line to the green line, and get to the airport much quicker. That's an emergent property of the subway system. So the better speed, the efficiency, is the emergent property of this subway system. Okay? So if you see this term, that's what it means, is an emergent property. Okay, sorry, we had to make a little bit of a cut there because I realized my PowerPoint was missing a few slides, my PPT. But I wanted to make a few quick points before we finish off. We're almost done. So just a few other big ideas from this chapter. One is that a system is comprised of storages and flows, so we're putting two ideas together. What is a system? But also when we show a system, we can represent it using storages and flows. This is one of the ways that we show information in this class. And these flows provide inputs and outputs of energy and matter. So when we see these arrows in our systems diagrams, that really means the flow of energy and matter. Okay, and I just realized I forgot to add the Chinese translation to this. Please forgive me, but yeah, we're gonna have to get past that. Now, finally, we have this idea of open systems and closed systems. Ecosystems are open systems. Again, like I said, most things are open systems. Closed systems are only experimental. They only exist in that situation. Now let's finish off. We got two more slides. When we were talking about flows, okay, these arrows, okay, again, they are matter or energy, okay. They can be either transfers or transformations. These are these words we saw at the beginning of this unit. So transfer is matter and energy moving without changing their form. So a change in location. So for example, this is like a food chain. When a small animal is eaten by a bigger animal, which is eaten by a bigger animal, what's happening? It's simply transferring the chemical energy from one animal to the next, and the matter from one animal to the next. That energy is not changing form, okay? Now, transformation is when that matter and energy does change form, okay? And we can see this with photosynthesis, okay? This is when solar energy is changed into glucose, or like sugar, basically, right? This is light energy becoming chemical energy. It's changing the type of energy it is. So we consider that a transformation. And again, these flows can show either transfers or transformations. And we're going to finish off with this. So like we just said, we have here a systems diagram, right? So we have storages, we have flows, okay? And you'll see we start off here with energy from the sun. It goes into these primary producers. Primary producers are like plants and algae. They produce energy. They produce glucose. That's why we call them producers. Primary means first. Okay. Well, that process, this arrow at the top, is a transformation. It's again changing from light energy into chemical energy. This arrow is a transformation. Now, every step after that is a transfer of energy. Okay? So now it's going from glucose to glucose to glucose to glucose. It's just going down. The matter is also transferring, transfer of energy and matter, but it's not changing form. So all these other three arrows are transfers of energy. Okay? So we go from primary producer to primary consumer. Consume means to take in, or in this case, like eat. Okay, so animals will eat plants, right? These primary consumers, we might call them herbivores, right? Primary, again, means first, first level. And then they are eaten by secondary consumers, okay? Also animals, but secondary means second. Then tertiary means third. These are kind of bigger animals that eat. But you will notice, well, let me finish off. We'll get to that point in a second. But what also happens to the energy, you'll see it goes elsewhere. So when you transfer or transform from one storage to the next, because it's not a closed system, because the body is not a closed system, it is continually losing heat. Okay, so you are losing heat loss with each step. Okay, so energy is being lost into the environment. Additionally, when these plants and algae die, when these animals die, what happens? They're eaten by decomposers. So that energy isn't just going to other animals, it's going to these bacteria, these fungi. Okay, they eat the dead animals. So the energy in this system, okay, let's say this is an ecosystem, part of that energy is going to decomposers. Okay, and again, one final point I want to make is that these arrows and these boxes are different sizes. So the biggest arrow is this arrow coming from the sun. Okay, we do that because it's the most energy. It's the largest amount of energy, whereas heat loss is a small little arrow. This is done on purpose. These systems diagrams often are drawn in a way where the biggest arrows show the biggest transfer or transformation of energy or matter. And then these storages do the same thing. The bigger the box, the larger the storage. So this, in this case, this is a storage of biomass. Okay, biomass. So mass means like weight or matter. It really matter. And bio, again, that prefix we learned means life. So it's basically the matter, living material. So plants and animals are made up of these chemicals that make up organic life. Okay, this is what we call biomass. The larger the box, the larger that storage of biomass, the larger the amount of biomass there is. And as we go down the food chain, that box gets smaller and smaller. Okay, so really the largest biomass box is typically primary producers. Smallest ones are these like top of the food chain carnivores, right? So the size of things, the size of the boxes and arrows show the amount of flow and the amount of storage. So that's the final point I want to make. Hopefully this one wasn't too confusing or too long. We'll get into 1.3 shortly, but otherwise, have a good day.